know, I figured an online semester would be easier. It just seems more difficult. What about for you all with all your classes? Does it seem like it's more work or same amount or less work?
So much more work.
Much more?
I think since they like
A lot more work.
I think since they took out all the breaks and everything, it's just like nonstop.
Yeah, it's just this one continuous stream that just keeps hitting me in the face.
Yeah, I feel the same
I
way.
feel like
Go ahead.
there's a lot less like structure on like a daily basis. It's like there's no like if I don't have a class, like this is my first class of the day, so like I feel like I can sleep in all day and it kind of leaves me feeling unproductive.
Yeah,
I
yeah.
also think without the cushion of being at the university and kind of living in the bubble that kind of is a university campus or around a university campus, it feels like there's more, I think, because we're experiencing more of everything that goes on around us.
Mhm.
Yeah, I think since we're at home, or I don't know, like not at campus, we tend to be less productive, a little less productive and not getting that college experience, but yeah.
It's hard to get in the mindset because you're immersed in a different world where this wasn't the expectation. Yeah.
Yeah, for me, it's just hard because, like, I don't know. I feel like I just stare at a computer screen for most of the day, and it, like, yeah, it's really, I don't know. It's like, it's not like depressing, but it's just like,
I don't know. I was driving 3 hours a day, every day, but to get to campus. So this whole at-home thing has made my life pretty easy for my last semester here.
Yeah, I'm
I
happy.
definitely feel like I'm getting more headaches.
What's that, Diego, was
I
it?
feel like I'm getting more headaches because I'm just staring at a computer screen like
Yeah.
all day.
You're spending a lot of time in front of the screen. Your classes, but like meetings and recording videos. If you're in the lab course, you know I'm still recording tons of videos. And it's just constant sitting, my butt's sore, my shoulders are sore, and just staring at this screen all the time. And then if there's anything extra, like I tried to do a grant earlier this week and I did it, but I'm just like exhausted. I need a week off. I need fall break to come, but there will be no fall break.
Dr. Riker,
Yeah, go ahead.
what do you do in your spare time to take a break?
What is this spare time? What is this?
Oh, no, I said, what do you do in your spare time? Just
No,
to
I know, I'm kidding.
go.
Like, I don't know what you mean by spare time. I try to, I spend time with family. I have 3 boys, the youngest in college, the oldest 2. Through marriage, they're done with college, but they live local. So family time, and we still squeeze some of that in. Also, I'm double teaching this semester. So what I do in the fall is I double teach, and I try to do all my grant writing. I try to squeeze everything in, and that frees up the rest of the year. So my springs and falls are very wide open. I have more time to do research with my students and work on other projects. But just right now, it's killer. Yeah.
Have you met Neil deGrasse Tyson?
I have. Yeah, I got that question a few classes ago. It might have been this class, might have been the other class, and I went looking for the picture. I have a picture.
Yeah, that was me.
And I think it's on my Facebook site. I don't think it's in my directories, but yeah, there's a picture of me and Neil deGrasse Tyson. He came to UNC to give a talk, and there's going to be a photo shoot outside, but it was raining, so he came up to my space because I have a telescope just mounted there for testing. It was a good backdrop, but the cost was a picture. So I got my picture with Neil deGrasse Tyson. Anyway, it is time to start. So let's see. Announcements. This is Wednesday, so tomorrow is Thursday, office hours. I'll be available for office hours before the exam. If you have any last minute questions, the exam becomes available at noon on Friday. I have not written it yet. I'll probably write it tomorrow during office hours when no one comes to see me. So that's how I'll spend the time. And it'll be due Saturday at noon. So noon to noon. No midnights, noon to noon. And then homework 4 is due a week from Friday. Any questions about any of that? Last chance to ask questions about the exam except office hours.
Hey, Professor, can you see again, when does exam start?
It starts at noon Eastern time in the US.
Oh, it's on Friday, right?
Yep, Friday, noon,
Okay.
seat time. Yep. It runs 24 hours. You can come and go. It's not timed, but you must be done by noon on Saturday.
Professor Reichart, for the exam, if we just save our progress or the answers, we should be fine, right?
Yep, you can save or you can submit. I'm going to set it up that you can submit each question up to 100 times. So now if you only use the save and forget to submit, you'll get a 0. They'll email me and I can submit your questions after the fact. The safest thing is just to use the submit button, unless you're planning on changing your mind more than 100 times for each question.
Okay, thank you.
I hope that's not the case. All right, anything else?
Is the exam on WebAssign or Sakai?
WebAssign, yep. It will be very much like the homeworks, except you don't get 3 chances. You know, you get no feedback. Whatever you submit last is what's graded.
Will we see our grade after we submit it or after noon on Saturday?
After noon on Saturday. Yep, you won't get any feedback because one person could take it early and get 100% and then distribute the correct answers. So you won't get any feedback at all until noon on Saturday. Then you'll get your score, and then like a day or 2 later, I'll post our first score to grade conversion spread. Just because the average scores on my exams tend to be around 70%, sometimes lower, sometimes higher. And that does not mean you got a low C or a high D. The average in this class is going to be like a B minus. By university regulations, I explained in the first class, I do have to hit a certain GPA overall. But once you get your score, don't necessarily freak out. Wait till you get the conversion, and it will be a spreadsheet that I post in the WebAssign area where you can enter your score in the exams and the first 3 homeworks, and it will give you your current rank in class.
And it's all multiple choice, correct? Just like the homework?
Just like the homework, even better, because in the homework I have some multiple selects. These will all be multiple choice. Anything else?
What chapters is the exam on from the textbook?
From the textbook, that would be 1 through 4. Lessons 1 through 3, which I think covered chapters 1 through 4. Anything else?
I have one question.
Go ahead.
What concepts do you think would be probably the most important to focus on when we're studying?
First and foremost, the concepts that I cover in the homework questions and the warm-up questions. So the exam questions will look very similar. They'll be different, of course, but like the math ones will be very similar, just different numbers, maybe names of objects. But first and foremost, the homeworks and the warm-ups. After that, anything I covered in lecture, and then beyond that, anything that's in the textbook. I would not spend your time rereading the textbook. If you've already read it once, that's probably sufficient. Instead, focus on your lecture notes. You can always go back and watch lectures if you want. I don't recommend you rewatch all the lectures either. Though if you do that, be sure to put YouTube on ×2 so it doesn't take so long. You can play these things back faster. That's how I prep. I watch my old videos of me teaching, but I have it on ×2 so it doesn't take so long. And but first and foremost, it's the homeworks and the warm-ups, and make sure you look at the answer keys as well. A lot of people go through the whole course and they don't realize that after the due date, you can press a button at the top and it will show you worked out solutions. Not just which one's the correct answer, but worked out solutions. Study that, you should be fine.
I have a quick question.
Yeah.
Are you going to post an answer key alongside the warm-up questions?
Yes. The warm-up questions have already been posted, actually, in the WebAssign area. If not, tell me, because I think they're posted now. And they're there. It's just a PDF, and every other page is a question, and every other page is a solution set. They're kind of brief. These are the ones that I do put up under the doc cam in class. Anything else? Not sure that was a question. I think that was background noise. Okay, you do that.
in WebAssign can we find the answer key?
Yeah, so you go to the homework and maybe under
For the warm-up questions.
Yep. Open up the homework questions, and right above question 1, there's a button saying, do you want to look at the answer key? And once you press that button, it makes a record that you've seen it. So if you were hoping to make some, excuse for like I was sick, couldn't do it, if you press that button, then you're ruled out from any special consideration. But just for studying, yeah, you want to press that button and look at those solutions.
What about for the warm-up questions?
The warm-up questions, it's just printed in the PDF. Every other page has a solution.
I mean, they're in WebAssign?
Yeah, they're in WebAssign in the announcement area when you log on. I put the link there Monday night, and so you can grab them at any point. There are a few questions in there that I did not get to during lecture, including the last one is, the last 2 are on the Doppler effect, so a little bit more math practice there.
Okay, thank you.
Anything else?
So what we've been learning this week with like reflection, refraction, that's not on it.
It's not on it. This is for the second midterm. I'm just making use of the classes.
Right. Okay.
I
Thank you.
normally try to finish it, lesson 3 early enough to give you time to study, but while you're studying, I move on. Okay, I will take that extended pause as the end of questions. I'll just mute y'all, but of course, feel free to unmute and interact. Let's take a look at our warm-up question. This one should be pretty straightforward. It's based on the material from last time where we started talking about telescopes and some of the advantages and disadvantages of reflectors and refractors. So the question is, which of these can only focus on one color of light at a time, which would be a disadvantage? Reflectors, 1 or 2 refractors. So let's see what you concluded. And yeah, most of you said 2, the refractors. They only focus on one color at a time. Here's the answer page. You saw it in color. But this is probably one that's worth seeing in color, so I can just grab it really quickly. I know I have it here. Here it is. And this was, I talked about 4 reasons why reflectors are preferred over refractors. Deficiencies of refracting telescopes, which is why well over 100 years ago, professionals have moved on to the reflecting telescopes. And this is just one of those 4. When light goes through glass, it refracts. That's why we call them refractors. But different wavelengths have different indices of refraction, different amounts of bending. Red refracts the least, so it focuses way out here. Blue the most, so it focuses closer in. There's no one distance that you can put your camera where all the colors are in focus. So what they normally do is they'll put a filter, like a red filter in front of the telescope or behind it, but before it goes into the camera, and they move the camera to the red focus. And if you want to image green, you put a green filter, move it to the green focus, and then blue, you put a blue filter, move it to the blue focus, but you have to keep changing the focal position. Okay. Just a little review, a pretty straightforward review from last time. Okay. So next topic is telescope design. And from this point on, we're mostly going to focus on the reflectors. Because again, for all the reasons I outlined last time, this is the telescopes professionals use. All those deficiencies of refractors can be overcome if you want to spend extra money, but you can do all these things better and cheaper with reflectors. And there are all sorts of different types of reflectors. So here are the 4 basic designs. Let me go through them and some of the advantages and disadvantages. So the first one there is prime focus. This is a common setup with professional telescopes. The light comes down, bounces off the mirror, and then comes up to the prime focal point, and that's where you put your camera. And it works well with professional telescopes because professional telescopes tend to be really big, and our cameras tend to be about this big. This does not work well on amateur systems, small telescopes, because The telescopes are about this big, and then the camera's about this big. The camera would cover the entire opening of the telescope, blocking all the light. So if it's professional telescope, big opening, small camera, you're only blocking a little bit of the light. And also, there are the support structures. The camera just doesn't float out there in space. You have to have connections to the side of the telescope. But as long as it's a big mirror, most light will still get through. So that's a good option for professionals. And it's used a lot if you want a large field of view. Putting the camera at this point, you can often get a larger field of view of the sky. That's prime focus, simplest type of reflecting telescope. Here we have Newtonian, and this is typical of amateur systems. Again, I said that, if you let the light come to prime focus and put your camera here or put your head in an eyepiece there, you block the incoming light. So what you do is you insert a small secondary mirror that redirects the light out to the side. And we saw an example of this last time. And then you can put your eyepiece here or your camera here. So it works well on small telescopes. But the bigger you make the telescope, the more inconvenient this becomes for the amateur. Suppose you have an amateur who's looking through it with an eyepiece. The bigger you make the telescope, then this location, it gets higher and higher off the ground. You need to get a ladder and climb up higher and higher to look into that eyepiece. Also, professionals don't like it because you're putting your camera on the side of the telescope. And then your telescope's out of balance. You have this extra weight on the side. You want the weight to be on the main axis. Again, these telescopes have to be exquisitely balanced. In all configurations, no matter where you point it, you have to have perfect balance because they're not just sitting there. Again, you're on a rotating planet. So these telescopes, as they're imaging, they have to move at the same rate as the planet in the opposite direction to counter out the motion of the Earth. And again, it's exquisite balance, and it requires, it gets much harder if you have a lump on the side of your telescope. So these are good for amateurs, but not really professionals. Then you have Cassegrain, and both amateurs and professionals use this. This is a good solution for both. If you're going to have this secondary mirror here anyway, it's blocking the light that would hit the center of the primary mirror. So, you're not using that part of the mirror. Even in this design here, once I insert a secondary here or here or here, I'm not using the center of the mirror. We talked about last time, this doesn't create a blind spot. It just reduces the amount of light that makes it in. But if it's a small secondary, that's not a big deal. And if you're not using the center of the primary mirror, you might as well just cut a hole in it and send the light right back down through it. You could put your eyepiece on the back of the telescope, or you could put your camera on the back of the telescope. It's on the main axis, so it's a good solution in terms of telescope balance. There's no weight on the side. It's on the main axis of the telescope. Also, as the telescope gets bigger and bigger, if you have a large telescope, you may not be able to get your eyeball up to the top to look through a Newtonian eyepiece, but you still have easy access to the back end of the telescope. The back end of the telescope is always low to the ground for the most part. And so you can put your eyepiece here, or again, your digital camera. So it works for all sizes, works for pros, works for amateurs. It's well balanced. So you see it a lot. The prompt telescopes. If you're in the lab using prompt telescopes, this is the design for most of the telescopes on Skynet. Oh, if you're in lab, I should say, COVID is getting better in Chile, and they're going to reopen our primary observatory in the Chilean Andes over the course of the next 2 weeks. So in a week or two, we should regain access to a whole bunch of our best quality telescopes, and you'll get to use those. And then our fourth design here is called Naismith or Coude. They're two different things, but they're kind of grouped here together. This is what you do if you have an instrument that is super heavy. It may be bigger than your telescope itself, and so you can't attach it to the telescope. It'd be too cumbersome. Some instruments that astronomers have fill entire rooms. So all telescopes have a rotation axis that's fixed, that points towards the North Star. The telescope moves around it. In this direction is declination. In this direction is rate ascension. what you can do is you can put a third mirror here that no matter how the telescope is oriented, it redirects the light down that axis. And then it may go down through the floor into a room below where you can have as much instrumentation spread out as you want. That's called coude. Naismith's kind of in between, where you're using a tertiary mirror to send it out to the sides. And I'll show you an example of that. In that case, the instrument doesn't ride on the tube, it rides on support structure. So it's for medium-sized instrumentation. Anyway, Naismith and coude is for big instruments. Okay, those are your 4/5 different designs. And this is a good example. This is my favorite telescope. I've observed with it twice. It's the Hale telescope. It's a 200-inch mirror. The mirror sits here. 200 inches is 5 meters. This is a Caltech telescope south of it's between LA and San Diego. It was the largest telescope in the world for about a quarter century, from mid-20th century to the late 1970s, maybe early 1980s, when Caltech then built the 10 meter and built two 10-meter diameter telescopes in Hawaii. Anyway, we can see everything here except Newtonian, because again, that's an amateur design. The light can come in, bounce off the primary, go all the way up to prime focus. Pretend, they can slip the tertiary mirror out of the way and the secondary mirror out of the way, and the light can go all the way up to prime focus. And yeah, that is a person. This gives you a sense of scale. Nowadays, you just attach a digital camera and don't worry about it. But back then, mid-20th century, we didn't have digital cameras. We used these giant sheets of glass with a photosensitive emulsion. They were made by Kodak. They're kind of like film, but they're on glass. And you'd have someone riding around in the bucket up there. It's called the observer's cage. This thing's like 10 stories tall. So imagine sitting in that little cage and the scope's moving all around and you're being tilted this way and that way. It would have been a wild experience. And the person is there with the piece of glass holding it into the focal plane, because the focal plane's not flat, it's actually curved a little bit. So you have to press the glass down and you expose, and then they reorient the telescope, you hand it off to a helper who's on a catwalk up above, they run to a dark room to expose it, and they hand you a new one, and off you go again. How they did things back in the day. This telescope, I mean, nowadays, a 5-meter telescope is not the biggest thing out there. In fact, UNC has a 4-meter diameter telescope. It's maybe about 1/3 of the volume. You can build these things much more compact. But back mid-20th century, it's kind of like in these movies where you see these, the insides of old clock towers with giant gears and systems that would be done much more compactly these days. It's just a blast from the past to use this telescope. It's still functioning. Well, you can slip in the secondary mirror right here, blocking off the observer's cage, send the light back down through a hole through the primary, and you can have instruments here. That's Cassegrain. And you can see there's a forklift, so you can get up there and change those instruments. Then you have a tertiary mirror that you can slip in, and you can send the light down the main axis, and the main axis points to the North Star. So if we kept going in that direction, that's the North Star. Down into a room below, that's coude. Or you can turn this tertiary mirror sideways, either in or out. You see these two support arms? This one's in cutaway. It's drawn in cutaway. And you can see the other one behind, but they're both full arms. And you can put medium-sized instrumentation in there. When I was a postdoc at Caltech, I spent maybe 3 days in the left arm. And the only thing I really remember about it is it's freaking cold in there. I was like shivering and freezing the whole time, because they keep it at a cold temperature. Anyway, you can point this mirror sideways and send it into instrumentation that rides in these support arms, medium-sized instrumentation. And here's what it looks like in reality. I figured I'd start with the schematic so you can see how the light flows. But here's the observer's cage. Here's the catwalk, where you can walk up there like 10 stories up. Here's the primary mirror, some people for perspective. Here's one of the support arms. There's another on the other side. Coude is off in this direction below the floor. And I only used it twice. I was training to be a theorist. And I only became an observer because of a certain theoretical prediction I made with my advisor in grad school. And I decided I wanted to build robotic telescopes and try to see it through. But anyway, so I didn't do too much observing, but a little bit. And I went out there twice. One time, the sky was clear, but so blurry we couldn't use it for science. So we just took pictures of Saturn like an amateur the entire night, using this gigantic telescope to image Saturn, which was kind of fun. And the other time, in the morning, the instruments that are up here in the observer's cage, they're cooled with liquid nitrogen. They perform better if you keep them cold. And so you have to go up and refill the liquid nitrogen. And they have a person whose job that is, but I went up with that person, figuring I'd jump in the cage just to say I've been up there. Though once you get up there, it's kind of a precarious ride. You're on a little elevator that's open that kind of goes with the curvature of the dome. And so you start getting vertigo as you're going up. And you walk across this catwalk. And then there's a 2.5-foot jump into the cage. And the cage is, really big. You're not going to miss it unless you jump really sideways and then you fall 10 stories to your death. Just 2.5 feet, but mentally I couldn't do it. It was too much. Fortunately, I didn't need to. I was just there observing. Fun telescope. Okay. There's another class of telescopes that's a hybrid between reflector and refractor. And these are called Schmidt telescopes. So I think I'll write that down. And they're used both by amateurs and pros for different reasons. So a Schmidt telescope, it has a mirror, but it also has a lens, what we call a corrector plate, a type of lens, corrector plate. So here's an amateur telescope, and even as an amateur system, that's probably a $5,000 system there. I'm glad I'm a pro and I don't have to pay for my telescopes, because even the amateur ones are really pricey. The prompt telescopes, the smaller ones, are about $100,000 systems each, paid for by your tax dollars, so thank you. But anyway, the mirror's in the back here, of course, but you see this covering at the top here. It's not just to keep water out. That is actually a lens of sorts. That's the corrector plate. And you need it because the mirrors in amateur telescopes are spherical. Now, we learned before that the shape that you want is a parabola. If you have incoming rays and you have a parabolic mirror, you focus to a common point. If you were to use a spherical mirror, it wouldn't focus. The light rays don't converge, and so you have a fuzzy image. But spherical mirrors are a lot cheaper to make. It's a constant radius of curvature. Let me draw it here. So again, here's the parabola. And the very bottom looks kind of like a sphere. I can draw a sphere in here. It just barely touches. And of course, we're only making this much. So the farther you get from the center, close to the center, a sphere is a decent approximation of a parabola. But the farther you get from the center, the worse it is. They're cheaper to make because you have a constant degree of curvature going around a sphere. So you can build an apparatus that smooths the glass at a constant rate, a constant curvature. You just keep changing the orientation. And so they're pretty cheap to make. Parabola, you have to change the degree of curvature of your smoothing device depending on where you are. So you can do it, of course, but it's pricier. So for amateur telescopes, they use spherical mirrors. In fact, often you can have your own kit. They'll send you a piece of glass and you can polish it yourself for days on end. It's just the natural motion of the human hand over it is kind of spherical polishing. And you send it back and they'll coat it and you can build it into a telescope. But you need a corrector lens to take the incoming rays and distort them in just the right amount that a spherical mirror will focus them. And that's why you have the corrector plate on the front. It's not just to keep the water out or to hold that secondary in place, but it is actually distorting the light to correct for the cheap-ass mirror you have. Now, so the reason amateurs use it is it's cheaper. The reason pros use it is you get a large field of view, FOV is field of view, without distortions. distortions, T-S, I don't know, tired. I think it looks right enough. Large field of view without distortions. Here's an example. This is about as large as professionals build these things. This is European Southern Observatory in Chile. And we use these to make surveys of the sky. At least we did decades ago. We have other telescopes that do it now. But let me draw what I mean by without distortions. Take one of our prompt telescopes that you're using in the lab. They are typically 1/6 of a degree across. That's a fraction, 1/6. A small field of view. Now, these Schmidt telescopes, you're able to have a large field of view. This is maybe a degree across, and some of these are like 2 degrees across. So you can image more of the sky at once without distortions. A normal telescope, stuff in the middle, you can get that in focus. Maybe there's a star, maybe there's a little galaxy, or in this telescope, here's the star, here's the little galaxy. You can get nice and in focus. But the farther out you go, you start to pick up distortions with the normal telescope. They can get pretty extreme as you get farther away. And the most common type of distortion is something we call coma, because it looks kind of like a comet. You have a head and the light is blurred, pointing away from the optical axis. So if I take this little piece of this field of view, I can show you what, it looks something like that. See how everything's distorted in the same way? The central axis is way up here somewhere. You're far from the axis and the light's distorted, pushed away from the central axis. But with the Schmidt telescope, you can have a large field of view without coma. It's just nicely in focus across the whole field. And that's useful if you're trying to map large regions. There are 2 ways to use a telescope. Maybe you know exactly what you want to look at, or you have a list. And you can have a telescope like prompt, and you point it, and you get a picture of that, and then a picture of that, and a picture of that, and you're good. But the other way you can do astronomy is you just map everything, collect the data, and then try to find the objects you're interested from your large survey. You don't know where your target is, but if you map enough of the sky, you'll find some examples. And so you have targeted astronomy, and the prompt telescopes are good for that, and you have surveys. And Schmidt telescopes, in the past anyway, were the best option for that. So let me see here. I think this is getting into the detectors, but I'll just pause there for a second. Any questions about telescope design? Okay. Now, and with the surveys, I should say, these Schmidt telescopes, we have like one in the north and one in the south. Back in the 60s and 70s, they did map the entire sky, and we used this map. In fact, I'll show you a piece of it in a second. Nowadays, we're building a telescope called the Rubin telescope in Chile, not far from the prompt telescopes, 1 mountain away, that will map the entire southern sky every 3 days. So the process is being sped up tremendously. And the goal behind surveys now is not just to map what's out there, but to find what's changing from night to night. The sky is a busy, changing place. So we call it time domain astronomy.
I actually have a question.
Yeah, go ahead.
So with surveys, would you not end up just wasting a lot of resources collecting insane amounts of data?
You do collect insane amounts of data. Petabytes of data, not terabytes, petabytes of data nightly. But we're then searching it to find things. And particularly, like with the Rubin telescope, things that change over a short period of time, like supernova explosions, moving asteroids, things that go bump in the night. That's the future of a good chunk of astronomy. And yeah, you have to collect tons of data, and so you're gonna have to spend the money on the computers to process it quickly. And it's not just about paying for the telescope. You're spending as much money on the computational back end. But then go ahead.
Sorry. So when the government begins funding less on NASA, does it make it harder to be able to actually get all these information to understand what you're trying to figure out?
Yes, with one caveat, and no one understands this, so it's okay. NASA, they only do space space-based astronomy. Anything done from the ground is paid for by the National Science Foundation. But I mean, that little detail aside, yeah, as funding is cut back to these agencies, it becomes harder and harder, and we have to make choices. The biggest ground-based project from the ground, you can do optical and you can do radio. And so there's one very large optical project, that's the Rubin telescope that I was telling you about. It's an 8-meter diameter telescope, map the whole sky every 3 nights, at least in the southern hemisphere. And there's a large effort in the radio called ALMA as well. And the large efforts in space are like the replacement for the Hubble Space Telescope, which is scheduled to be launched in 2013. But you know, because of delays, maybe we'll get 2023. We'll see. And as we venture into these new areas, we have to close down older telescopes. So nowadays, 4-meter class telescopes are the ones being closed down or no longer funded by the government, and they put the money towards the cutting edge. But it's not much money either way, you know, and a lot of people will make the case, why should we spend any money on astronomy when people are starving, and things like that. And I understand those kinds of arguments, but it's important to keep in mind this is a very, very small fraction of the national budget, well below like 1/10 of 1%, that kind of thing. Even most of the money that goes to NASA, very little of it goes to NASA astronomy. A lot of it goes to low Earth orbit launching and eventually Moon and Mars. Okay, so let's see, next topic is detectors. So we've talked about the different designs for telescopes. So now let's talk about the detectors. I'm checking the time. Yeah, we're good, okay. Detectors. So, you know, before the 1920s, it was just your eye and then drawing with your hand and eye. So hopefully you have some artistic skill and you can draw well what you're seeing with your eye. That's what we're limited to. But between the 20s and the 70s, the primary technology was these photographic plates that I just mentioned. This is my former postdoc, Aaron Laclouzet. He's now a professor at University of Michigan, but he helped me build many of the prompt telescopes at Central Michigan University. And he's holding one of these glass plates that, again, they were made by Kodak. You have a photosensitive emulsion on it. You have to use glass because the focal plane is curved a little bit. So you want something that will bend. And so a thin thing of glass, you can bend it without breaking, but they're pretty fragile. I only have a few of them. Most of the ones that, you know, when I took over Moorhead Observatory, the campus observatory, there are quite a few. Most of those we've sent off to be archived and preserved. I kept a few. And here you can see one. You have to put up some light behind it to see what's on it. It's imaged in the negative, but here you see a galaxy and some stars. Now, you know, since they're quite fragile, and this was before the internet, what would happen is every university would get a full copy of the sky, not on glass, but a copy made on plastic. I have a couple of these here that I pulled out of UNC's copy. UNC still has it. I've moved it into a closet no one goes to because all of this has been scanned as online and easily accessible. But I think I can show you. Let's see, I'll put up the doc cam, put up Microsoft Paint, because you need a backlight. I'll move you all out of the way. And I'll point the doc cam at my other monitor. And it's upside down, I know, but it doesn't matter because there's no up in space. So here's a region with a lot of nebulosity. Now, a lot of these are just really boring, just stars. But this is a star-forming region, so you have a lot of structure, a lot of detail. What's on this one? Again, more nebulosity, some bright stars. Anyway, and so it used to be that if an astronomer needs to know what's in that part of the sky, they'd find that piece of plastic, put it on a light bench, and look at it with an eyepiece. Let's see, I've lost you all. I got to bring you all back up. Where's my mouse? There you are. Now, and again, that's what I was talking about. That's what they used to use up here in the Hale telescope and others. Come the 1970s to the present day, we switched over to using something called CCDs, though these are now being transitioned to what we call CMOSs, but they're both basically the same idea. It's a digital camera, and this doesn't look like much, but it's a detector of a digital camera. You have these things in your cell phones, just ours are much more sensitive. If we look at it under a microscope, you see all these little cells. And these are cells, imagine the light coming through the telescope, they're entering the camera and getting onto the detector. And let me just draw, so you know the terminology. You have the detector, maybe it's a CCD. The electronics you build around the detector is what we call the camera. But the CCD is the detector itself. And I'll often just still call them CCDs, although we're transitioning to a slightly different technology, these CMOSs. But the light comes in and it strikes the detector, and the photon knocks an electron off into what's basically a little electronic bucket. So we're not actually counting the light, we're counting the electrons. And some of these are really efficient, like 80, 90, 95% efficient. But we don't get, all of those photons don't get converted into electrons. There's some efficiency, there is some loss. And then they sit in these buckets, and you can't overflow the bucket. If you're looking at something really bright, the charge will overflow and will bleed out. Now on CCDs anyway, they bleed out in a linear fashion. You may have seen this if you've taken your cell phone and pointed at the sun. Ever see the straight lines that come out of it? That's charge bleeding out on the up-down axis. Then you have electronics here that reads out a whole row. And then like a bucket brigade, all the rows pass their charge to the next row up, and then you read out a row. And then they pass their charge and you read out a row. And it can take a couple seconds to read out one of these cameras sometimes. But they're very good at passing charge without losing it. They're very good at reading charge without losing it. There's a little bit of uncertainty, and astronomers call that read noise. It's responsible for some of the blurriness in your image, but it's usually a small amount. Now the CMOSs, they're different. They pull the charge out of every pixel simultaneously. Imagine little wires connected to each of these pixels, and you can just get all of it at once. So much faster. You don't have to do the bucket brigade. So that's kind of the new technology. And CCDs, I can't buy them anymore. They just sell CMOSs now. And once it's read out, it's digital. It's just numbers. How many charges were in that cell? So you can plot a region and you can put in some numbers here. The numbers are hard to look at. We'll often color code it or put a grayscale on it. In this case, we like to use white for a lot of counts and black for not very many counts because space is black and stars are bright. And that's how we create a digital picture. Now, that is a grayscale, a black and white digital picture. And astronomical cameras are all black and white. Your cell phone camera works in color. And that's basically because each one of these cells is broken into three parts: a red sensor, a green sensor, and a double-sized blue sensor. So in each region, you measure some red, some green, some blue, and the computer can merge that together into a color, just like we talked about before. If you have similar amounts of red, green, and blue, it makes it white. If you have more red than the others, it's reddish, more blue than the others. Maybe you have a thermal blue. But that's not good for astronomers, because astronomers are trying to measure, like, how bright is the star? And we want to know, how bright is it in red, for example? Well, I don't know how bright it was in red under the green and blue sensors, or how bright it was in green under the red and blue sensors, etc. So we just have one type of sensor. And if I want to look at red light, I put a red piece of glass in front of the camera, kind of behind the telescope in front of the camera. We have a filter wheel. It's a wheel where I can rotate different colors of glass. And this isn't like random glass I picked up out of the trash somewhere. It's very exquisitely designed to match a particular wavelength range, so we understand scientifically what we're measuring. So if we make a color picture, whenever you see a professional astrophotographer or astrophotography, we have astrophotographers, right? You see a professional astronomer's picture of the sky, astrophotography. They didn't take one picture, they took 3 pictures. They put a red filter in and made a black and white picture of red light, then a black and white picture of green light, and a black and white picture of blue light, if they want it to look like it would to the human eye. And then you can combine it. Here's just an example. Here we have some fruit, a lot of red fruit. So here's the red filter. Whatever is red in the combined image is very bright in the black and white red image. There's also some green in here, so that's lighter in color in the green filter. Things that are white have red, green, and blue in it. So like in the blue filter, there's nothing in here that's blue, but the white objects have blue in them, so you see some light there. The purple sheet has some blue, so it's a little bit lighter. And so this is kind of how it works with the sky. We black and white picture of red light, black and white picture of green light, black and white picture of blue light, and then we combine it. Though we don't have to restrict ourselves to the red, green, and blue filters of the human eye. We can pick any 3 filters. We can pick 3 filters in the infrared and make the long wavelength one, color it red, and the short wavelength color it blue, and we can make an image of what it would look like if our eyes worked in the infrared or the ultraviolet or the radio. A lot of the pictures you look at are taken at wavelengths the human eye can't even see, but we still take them in 3 different bands because the human eye uses 3 bands. The long wavelength we color red, the short wavelength blue, the in-between green, and hence a color picture. Okay. Now just the sensitivities. The photographic plates, that's what we have here on the left, were not very good. 98% of the light did not trigger the photosensitive emulsion. So we're throwing away 98% of the light. We call that 2% efficient. Put the doc cam back up and I'll put some numbers here. These photographic plates, they're about 2% efficient. You're losing 50 times the light that you're getting. And the CCDs, depends on what you're buying. They can be anywhere from 50% to maybe about 95% efficient. There are different types of them. And the ones I buy for most of the telescopes are 90% efficient. So you're getting almost all of the light. And here's the difference. This is the exact same field, the exact same exposure time. Maybe they're observing for 1 minute, but you can see so many more stars using the CCD or the CMOS. And that's, you know, when this technology came out in the 70s, it's like if you're getting 50 times the light, it's like you have 50 times the collecting area. You have a telescope with a mirror with 50 times more collecting area, except you didn't have to build it. You just changed the electronics on the back end. And it was as if your telescope got 50 times bigger in terms of its area. So that was a huge advancement. And then here you see an example of color combination of 3 CCD frames. And some of the stars are red and some are blue. As I said, the universe is a super colorful place. Okay, I'll just pause for a second for questions. Then I'll start the last topic. Okay, last topic. And I probably can't get through the whole thing, but I can get it started. No, we did detectors. 1 second here. Oops, let's get this up. Next topic is spectrometers. So we learned the importance of spectroscopy. So astronomers build devices that can detect a spectrum, and they're really simple. It's a 2-component thing. You have a disperser and you have a detector. And so here we see an example. Here we have just light going through cold glass or a cold gas. So we should expect an absorption spectrum, a continuous spectrum coming from the light bulb here. If that's cold gas, we'll get an absorption line spectrum. And then in these spectrographs, we block everything except a slit, let 1 slit of light go through, and it enters a disperser. So here's the simplest type of disperser, the one you're most familiar with. That's a prism. And as we know, the red light will get refracted less and the blue light more. And so it comes over here to the screen and it's spread out, and that's where you put your detector. So you have a disperser, in this case, prism, but we don't use those very much in astronomy. And the detector, it can be anything. It can be a photographic plate back in the old days. It can be a CCD or a CMOS camera, a digital camera in the new days. And here's an example. This is actually a photographic plate, imaged in black and white. And this one's reversed from the picture. And this one, blue is on the left and red is on the white. And you can see all those absorption lines. And all we have to do is look at, those emission tubes that I had a few classes ago, and you saw the lines. We shine one of those into a telescope, and it tells us what part of the detector corresponds to what wavelength. Like if I do the hydrogen one, I know Balmer alpha is 656 nanometers. It lands somewhere, and that tells me, okay, over here's 656, over here's this, over here's that. So I can calibrate the detector, and then I can send in light from astronomy, and here we see a lot of iron and chromium, absorption lines, some other things as well. And then we can read the wavelengths off of it and the intensities. Let me go 2 minutes over just so I can finish this topic today. There are other types of, so we know all about the detectors. We just talked about that, but there are other types of dispersers. And the primary other type of disperser is a grating. Here's an example of that. That's what I used the other day to disperse the light. I held it up to the camera and we got some color dispersion in there. You can almost see you see it in action right there a little bit. And this makes use, it's basically Young's double slit experiment. Except instead of one slit, there are many slits. And the light's going through, we have the primary band and then the first order, second order, and so forth. The thing is, for each order, in the 0th order, the primary straight through, all the light just goes through straight, and it still combines and gives you whatever color it was. But in each of these orders, they spread out. The blue light, it's a little bit closer in. The red light, it's a little bit farther out. And so that's all that this is. It's a bunch of little grooves. It's a Young's double slit experiment. And the spectrum that you were looking at was first order. It's the light just stretched out a little bit. And it's made, actually, I don't even have to cut all the way through, just little grooves. So under grating, call this a transmission grating. And one type is called relief, where you just cut the grooves, and it's basically a Young's multi-slit experiment. The other type is VPH, where you don't cut grooves, but you put a surface on the glass that has a varying index of refraction. And it basically acts in the same way. I'll write that on the doc cam, VPH, volume phase holographic. And these are the best by far. In fact, UNC is one of the leaders at doing this. I have an example that I stole from the VPH lab 10 years ago, but it doesn't work anymore. So here's a picture of how it works. You shine the light through it, and it's going through this film on top of it that acts like a grating, acts like a Young's multi-slit experiment, and then the light is spread out that way. And the last example I'll show is the relief gratings you can do in reflection. So we have transmission, you have reflection, because sometimes when building these spectrographs, we have to fold the light. It has to bend back and forth a couple times to stay in the device. And so often we'll have a grating that the light doesn't go through, but it bounces off. And a good example of that is actually just the back of a CD, where they cut all the grooves in where they encode the music. But you can see, just me moving it under the light here, how it's breaking the light up into a spectrum. This was never designed to be an astronomical element, but you get the idea. So astronomers will use prisms sometimes, but the gratings are more efficient, and we usually use either a relief or reflection grating, or if you want to pay out the big dollars, a VPH grating's the best. It disperses the light, then you can detect it with your photographic, well, we don't use those anymore, but with your digital camera. Okay, I think that went about 3 minutes over. Yeah, that's it for today. I'll stick around for questions. Otherwise, good luck on the exam on Friday and Saturday.
Can you go back to the detector slide of like the paper?
Yes.
Thank you, Dr. Ecker.
Sure, my pleasure.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
What is the 50 to 95%?
That's the efficiency. That means how much the light, the incoming light, is actually detected, actually triggers something in the detector. Photographic plates, most of it just goes through the glass. It doesn't trigger the film on it. But with CCDs, you can capture almost all the light if you're willing to spend the big bucks.
Also, I just wanted to say, I'm in the lab right now, and I took like colored images and like layered them and made like fully colored images, and it was really fun.
Yeah, that's what people want to do most. And we will be adding that functionality to Afterglow, so you don't have to go to like Photoshop or wherever you happen to go. We will be adding it to Afterglow. But I can't make it part of the lab because it eats up a lot of telescope time. Now, you probably wanted to look at a nebula or a galaxy, so those are longer exposures, and you had to do 3 of them. And if we have like 5,000 people across the country doing it, it eats up a ton of telescope time. So we leave it to just the few who are interested enough to venture off on their own and do it.
Yes, it was really cool to do that.
Good. And what did you do it for? What was your object?
I did the Helix Nebula and the Eagle Nebula.
All right. Yep. The Eagle Nebula probably came back very red.
Yeah, it was like pink and purplish. It was really cool.
Mm-hmm. And a lot of that is line emission from hydrogen. Yeah.
I think that's what my TA was telling me, because I was like showing it to him and he was like, it should be pink because there's a lot of hydrogen.
Yep. H alpha, Balmer alpha. Yep. That's that one red line we learned about. That's primarily what you're seeing spread out across that image.
That's super cool.
Yeah. Now, we also have on the telescopes H alpha filters. So this is a filter that lets through only H alpha, and we have some that let through like only oxygen and only sulfur. Those are kind of the common lines. And a lot of astrophotographers will use those narrowband images. They don't bring in a lot of light, but it's centered on the emission line and to enhance their images. And if you are interested in astrophotography, let me just bring up one more thing that I think you'll like. It's on my homepage. Basically, these telescopes that you're using have been used by professional astrophotographers. They pay because they're not doing short exposures. They'll do like 4 hours of blue, 4 hours of green, 4 hours of red. But let me see here. Under prompt astrophotography, these are images they did with the same telescopes. So you can see the kind of the quality they can achieve if you have the money to purchase like 10, 20, 30 hours of observing time. And here's the second astrophotography group. And these are, each one of these became an astronomy picture of the day. It's, if you're not familiar with it, it's the most popular astronomy site on the internet. NASA does it. They pick one astrophoto per day and put it up there.
That is super cool.
I had a quick question about the information that's going to be covered on the exam.
Yeah.
With the one that has like the 2 masses, when you're trying to find like the force of gravity as the masses change, what does the r squared in the denominator stand for again?
The distance between the 2 objects. I know it's a little
So if it,
why didn't they use D? But they use R.
okay, I just wanted to clarify that. Thank you.
Yeah. Anything else?
I had an incredibly off-topic question of
Like when you're interacting with other astronomers in other countries, do you normally run into people who know English, or do you often have to hire a translator?
Everyone seems to know English. So we're lucky in that sense. It is the international language of science. And since I can only speak English, I'm fortunate. But I could go to international conference and do just fine. Unless it's like a local conference in another country, they may use their local language.
Okay, thank you.
Sure.